Okay, let's have a look at these properties of complex conjugates a little bit more closely. We mentioned a couple of them the other day, basically saying, we could multiply first and then find the conjugate or vice versa, those sorts of things. But some other ones, now that we've got some more terminologies, the modulus of z must be the same as the modulus of its conjugate. Because remember, the only difference is the sign of the imaginary part. So when we square it, it's going to give the same amount. So that's the first relationship there. With the argument, though, because the imaginary part is different, whatever the argument is of z, then it'll be negative for the argument of the modulus. And remember our picture we saw, there were reflections in the x-axis. So one would make a positive angle, one would make a negative angle, but they would be the same size. I've talked about this a lot now. So z times z conjugate is that sum of two squares, which happens to be the real part squared plus the imaginary part squared. And then another way we can write it now, because we know the modulus of z, we could call that the modulus of z all squared. And these are the ones, we saw the other day. So addition, we can find the conjugate of the addition first, or we could find the conjugate of each individual part and add them. Same with multiplication, same with division. I didn't worry about subtraction because, of course, addition is the same as subtraction. It's just you're adding a negative number. And the reciprocal one. So want to find the reciprocal of a complex number, it's the conjugate over the modulus squared. Conjugate over the modulus squared. So just an interesting little question here. If x plus iy is the square root of 6 plus 2i over 3 minus I, show that x squared plus y squared is equal to 2. Now, there's a really long way of doing this. But if we use conjugates, there's actually a very quick way of doing this. All right, so this is what they've told me. X plus iy is the square root of that particular expression. So x plus iy squared must equal 6 plus 2i and 3 minus I. I know that. But the conjugate of both sides must also be equal. But going back to the idea of, do I find the conjugate first or do I find the conjugate after the division and so on, I could rewrite the conjugate of 6 plus 2i and 3 minus I is just the conjugate of 6 plus 2i on the conjugate of 3 minus I. And I could also say, conjugate of x plus iy squared, I could find the conjugate of x plus iy first and then square it. And so I get x minus iy squared is 6 minus 2i, 3 plus I. So I've got these two equations. I'm just going to multiply them together. Now on the left-hand side, I'll get x plus iy squared times x minus iy squared. Conjugate times itself will be the sum of two squares. And you'll notice the fractions are also ended up being the conjugates times itself. So I will end up with x squared plus y squared squared is 36 plus 4 or 9 plus 1, which works out to be 4. So therefore x squared plus y squared is 2. Can't be negative 2 because x and y are real numbers and you can't square real numbers and get a negative. So that's a quick way of doing it. The long way of doing it is actually going and creating algebraic fractions with x plus iy and solving simultaneous equations. And it does eventually come out, but it is significantly longer solution than what we've got there. Okay, so 4H, which is in Patel, just 6 questions there to have a look at, playing with this idea of conjugates.